Welcome to my channel. Welcome to Brandon. So in this video I'm going to talk about the circuit response of series and parallel RLC circuit in frequency domain. So in my previous video I have discussed about circuit response to sinusoidal input in for the series RLC and parallel RLC circuit in time domain. I have derived the circuit response equation, especially the circuit response equation for the steady state part. So here I'm gonna also focus on the steady state response, not the transient response of the internal circuit, the internal system, uh, and the transients introduced by the input excitation. I'm mainly gonna focus on the sinusoidal steady state response of the circuit. Okay, so in Laplace domain this becomes the RLC circuit becomes like this. It is linear, but the L and C are transformed. So inductor has SL and capacitor has 1 by SC. So what I'm gonna do is I'm gonna apply KVL because this is linear transformation, and I can in Laplace domain or complex frequency domain the KVL KCL are valid. So by KVL I have VR plus VL plus VC equals Vs the magnitude by s square plus omega square. So if you look at the Laplace transform of sine omega t, you will see that the formula is omega square by s square plus omega square, and Vs is the magnitude. So Vs is IR plus VL is ISL plus VC is I by SC, which is equals to Vs omega s square plus omega squared. So if I take common L by S common, I will get S square plus R by LS plus 1 by LC I, which is function of frequency, which is Vs omega 1 by s square plus omega squared. So if I take this term to the right hand side, it will give me is equals Vs omega by L, then S by this full term S square plus R by L S plus 1 by LC. So this full term is called the characteristic equation in frequency domain for the RLC circuit, which is the second order differential equation, and S square plus omega squared. Now what I'm gonna do is I'm gonna take this characteristic equation and I'm gonna rearrange it. So the characteristic equation is S square R by L S plus 1 by LC, which is equal to S square plus, if I write it like this, so R by 2 root over C by L 1 by root LC plus 1 by LC. So this will become S square plus 2. So this is the damping ratio for the series RLC circuit, and 1 by root LC is natural undamped frequency, and S plus this is omega n square, sorry, undamped natural frequency. So this becomes like this. And now if so I want to find the roots of the second order characteristic equation. So for that, also the damping coefficient is r by 2l, which is the psi or zeta, how may you want to pronounce it, and omega n. So if I wanna take, if I wanna find the roots of this characteristic equation, so it will be like, so by the formula of the second order quadratic equation, to find the root, the formula will give me minus 2 zeta s or psi s omega n, okay, plus minus root over b square, which is 4 zeta s square omega n square minus 4 omega n square b square minus 4 ac by 2a. So a is 1, so 2.1. So this will give me, so zeta or psi s omega n is the damping coefficient. So if I take 2 out, so it will give me 2 minus damping coefficient sigma s plus minus, so here, so if I take omega n and 4 common, so and then 2 common from the full, so it will give me, so omega n root over, so if I change the position of this two, it will give me a j or I, a complex number. So this will be 1 minus sigma s square, psi s square, okay, by 2. So minus sigma s plus minus j. So this is the damped natural frequency. So this is damped natural frequency, where omega d is omega n root over 1 minus this, so psi s. So we have found our roots. So if I denote this by lambda 1 and lambda 2, so the root will be s minus lambda 1, s minus lambda 2, where lambda 1 is minus sigma s plus j omega d, lambda 2 is minus sigma s minus j omega t. So now what I'm gonna do is replace these values in the equation, find, so I'm gonna decompose this into partial fractions. So vs by l, so say a by s minus lambda 1 plus b by s minus lambda 2 plus cs plus d by s squared plus omega squared. So now I have to find the arbitrary constants. In the numerator there is s. So to find abcd, let's try it. So s equals a s minus lambda 2 s squared plus omega squared plus b s minus lambda 1 lambda 1 s squared plus omega squared plus cs plus d s minus lambda 1 s minus lambda 2. So if I am just doing it in shortcut, if I rearrange this, it will be like this. So a plus b plus c s cube minus a lambda 2 plus b lambda 1 plus c lambda 1 lambda 2. Lambda 1 lambda 2 are eigenvalues, interestingly. So s square plus a then so basically this is the rearranged form. Now what I'm gonna do is I'm gonna equate the coefficients of s cube s square s and the constant. So it will give me, so a plus b plus c equals 0. Then I'm getting a lambda 2 plus b lambda 1 plus c lambda 1 plus lambda 2 minus d equals 0. Then I'm getting a omega squared plus b omega squared plus c lambda 1 lambda 2 minus d lambda 1 plus lambda 2 equals 1. Okay, so it will be 1 because here there was s in the left hand side. Okay, so this and the last is a lambda 2 omega square plus b lambda 1 omega square minus d lambda 1 lambda 2 equals 0. So here c is obviously minus a plus b, and if I see that d is minus a lambda 1 plus b lambda 2, so this is easily the case. And so a omega square plus b omega square minus, this is minus, so I have c, so a plus b lambda 1 lambda 2 minus, so this will be plus, so a lambda 1 plus b lambda 2, lambda 1 plus lambda 2 equals 1. So we are left with a and b only. So I just have to rearrange this. So I'm not doing the extra part, I'm just going straight to the final relation. I hope you understand what I am doing here. So in this case, so minus a lambda 1 lambda 2 will be cut out by plus a lambda 1 lambda 2 and b lambda 1 lambda 2. So it will leave us with only, so a omega squared plus b omega squared and plus a lambda 1 square plus b lambda 2 square, which is equals 1. Now a omega square lambda 1 square plus b omega square plus lambda 2 square equals 1. A lambda 2 omega square plus b lambda 1 omega square plus d lambda 1 lambda 2. So if I substitute with the value of d, so it will give me plus a lambda 1 plus b lambda 2, lambda 1 lambda 2 equals 0. So if you look carefully, this will give me a lambda 2 is omega squared plus lambda 1 square plus b lambda 1 omega square plus lambda 2 square equals 0. This will give me obviously minus b lambda 1 lambda 2 omega square plus lambda 2 squared by omega square plus lambda 1 squared. So if I take the value here, so this will give me, so minus b lambda 1 lambda 2 and omega 1 is omega square plus lambda 1 square will be cut out by the by this in the denominator. So it will leave us with omega square plus lambda 2 square only plus b omega square plus lambda 2 square equals 1. So if I take b common, so if I take b common, it will give me like something like this, minus lambda 1 minus lambda 2, then omega square plus lambda 2 square equals lambda 2. So this now gives me b equals minus lambda 2 by lambda 1 minus lambda 2 in the denominator, omega square lambda 2 square. So this is the expression for b. Now I have to find the expression for a, c and d, among which c and d are of most importance. So a is minus b lambda 1 lambda 2 omega squared plus lambda 2 squared by omega squared plus lambda 1 squared, which will give me minus and minus plus lambda 2 lambda 1 minus lambda 2 omega squared plus lambda 2 squared. Okay, then lambda 1 lambda 2 omega squared plus lambda 2 squared, omega squared plus lambda 1 squared. This cut out, this cut out, so will leave me with plus lambda 1 by lambda 1 minus lambda 2 omega square plus lambda 1 squared. So this is the expression for A. So C is minus A plus B, so minus lambda 1 by lambda 1 minus lambda 2 omega square plus lambda 1 square minus lambda 2 by lambda 1 minus lambda 2 omega square plus lambda 2 square. So this will give me minus 1 by lambda 1 minus lambda 2. Then so if I take the multiplication, so here what I'm doing is I'm taking the multiplication, and so I am making this 1 into 1, so this will be, so omega square lambda 1 omega square lambda 1 plus lambda 1 lambda 2 square minus omega lambda 2 minus lambda 1 square lambda. So this will give me lambda 1 minus lambda 2. So if I take common, omega square minus lambda 1 lambda 2 into lambda 1 minus lambda 2 omega square plus lambda 1 squared square. So here omega squared obviously plus lambda 2 squared, so this and this cuts out, leaving behind omega square minus lambda 1 lambda 2 by omega square plus lambda 1 squared omega square plus lambda 2 squared. So D was initially expressed as minus A lambda 1 plus B lambda 2, isn't it? Or wasn't it? So if it was, I'm just gonna take the shortcut, so minus lambda 1 lambda 2 and lambda 1 squared by omega square plus lambda 1 squared minus lambda 2 squared by omega squared plus lambda 2 squared. So this will give me minus 1 by lambda 1 minus lambda 2 and omega square lambda 1 square minus lambda 2 square by omega square plus lambda 1 square omega square plus lambda 2 squared. Now so omega square lambda 1 plus lambda 2 by omega square plus lambda 1 squared omega square plus lambda 2 squared. Now I have found all the arbitrary constants in the partial fraction of the equation. Current response is Is, V is the magnitude omega by L, yes, so it was A by S minus omega S minus lambda 1, so A is lambda 1 by lambda 1 minus lambda 2 omega square plus lambda 1 square s minus lambda 1, then minus lambda 2. This is b by s minus lambda 2, so the expression for b is lambda 1 minus lambda 2 omega square plus lambda 2 squared s square plus s square, sorry, s minus lambda 2. Then d is minus, sorry, cs is omega square minus lambda 1 and lambda 2 s by lambda 1, sorry, lambda omega square plus lambda 1 square omega square plus lambda 2 squared, again minus. So there is no end to it, so omega square lambda 1 plus lambda 2, and oh, I have forgotten, so okay, let me write this first. This lambda 1 square, then omega square plus lambda 2 squared, and which is by s square plus omega squared. So this is the full expression. So I am to tell you this part, this first and second part. So this introduces only the transient introduced by the input, so I'm not gonna bother with this. I'm just gonna uh, keep myself in this section will reveal the steady state part of the response. I'm not going to derive the part for this. If you want, you can derive this yourself, but I'm just gonna occupy myself in this in solving this part. So I is for this part, the second part, so say it as 2. So okay, so v is omega by l. If I take the common out, so 1 by omega square plus lambda 1 squared omega square plus lambda 2 squared. So what I'm getting is, so if I take the minus common, so there will be a minus, and now omega square minus lambda 1 lambda 2 s by s square plus omega square plus omega lambda 1 plus lambda 2 omega by s square plus omega square. So this has become already become a standard form. I just have to rearrange this, okay, cleverly. I just have to rearrange this cleverly. So what I'm gonna do is, let's take the inverse Laplace first. So I2 is, which will give me IT. So IT is minus Vs omega by L and omega square plus lambda 1 squared omega 2 square plus lambda 2 squared and omega square minus lambda 1 lambda 2. So this will become cos omega t plus omega lambda 1 plus lambda 2. This will become sine omega t. So we're almost there, okay. So let us first find lambda 1 minus lambda 2. This will give sigma s. So this is the damping coefficient for series RLC circuit, plus j omega d minus minus sigma s minus j omega d. This will give me so 2 j omega d, and lambda 1 plus lambda 2 will give me sigma s minus plus j omega d plus minus sigma s minus j omega d. This will give me minus 2 sigma s, then lambda 1 lambda 2. This will give me uh, minus lambda s plus j omega d minus j omega d sigma s squared. So here this term cuts out, and omega d, if I decompose omega d, it will give me so sigma s squared plus omega n square minus sigma s squared. So this will also cut out, leaving us behind omega n squared. So lambda 1 lambda 2 is omega n squared, this term. So omega square plus lambda 1 square into, so before all this I have to find the value of this term. Now what I'm going to do is, so if I just multiply the two, so this will give me omega 4 plus lambda 1 square plus lambda 2 square omega square plus lambda 1 lambda 2 whole square. So this will give me omega 4 plus, so if I use the formula for a square plus b square, it will give me a plus b whole square minus 2ab. So lambda 1 plus lambda 2 square minus 2 lambda 1 lambda 2, with now omega square plus, so this is omega n4, so omega n4 and so omega 4 plus lambda 1 plus lambda 2 give me 2 sigma s minus 2 sigma s, so it will become 4 uh 4 sigma s. If a sigma s, just let me write that first, sigma s squared. Now so this is 2 omega n squared. Okay, omega squared plus omega 4, just let it be omega n4, sorry, so 4 omega n. So now if I rearrange this, this will give me 4 okay, 4 sigma s square omega square plus omega 4 minus 2 omega square omega n square plus omega 4n. Then 4 cross, if I decompose this, so sigma s is r by 2l, so this will give me r square by 4l square omega square plus this will become minus omega n, omega square minus omega n square whole square. Now this 4 cut out, so this is r square l square omega square. So if I take omega by l out from this term, so this will be omega square l squared omega l minus 1 by omega c. So omega square by l square, this gives me r is, so there is a square, so r squared plus, so this is x obviously in reactance, so x squared, which is omega squared by l square, the magnitude of the impedance. So I have found something very interesting and important. Now I'm just going to substitute it for this term in the main equation. So our steady state part, say 2, in the current response equation is Vs omega by L 1 by omega squared lambda 1 squared omega squared plus lambda 2 squared omega squared minus lambda 1 lambda 2 cos. So I had done the Laplace inverse Laplace transform, so this will become ISST. Obviously I there so if I take the inverse Laplace transform, the second part of the current response in frequency domain, this will give me the steady state response. So cos omega t plus omega lambda 1 plus lambda 2 sin omega t. So now I'm very close to the answer. So here v omega l, and this term is 1 by omega square by l square magnitude, then this is omega square minus omega n square cos omega t. There is a minus, if I recall there was a minus, so now here omega, so lambda 1 plus lambda 2 is minus 2 sigma s, so this will give me minus 2 sigma s sin omega t. Now what I'm gonna do is vs l by omega z squared, and if I take omega so let me do it like this first. So if I take omega by l common from this, so omega by l, it will leave me with omega l minus 1 by omega c cos omega t minus, so this is obviously omega by l, so after substituting for the value of this, what is this called, the damping coefficient, the equation looks like this. And now what I'm going to do is I'm gonna take minus omega by l out common, so this will give me so this a, okay, so let me first take the minus common out, so vs l by omega z squared cross minus omega by L, and this will become R sine omega t minus omega L minus 1 by omega c cos omega t. So I have found that this cuts out, so leaving me with, so now what I am left with is Vs, the magnitude by the impedance, the amplitude of impedance squared. And if I take this, so R is sine cos phi. If you have seen my time domain video, I have already discussed this. So R is the magnitude of the impedance cos phi z sine omega t minus, this is the reactance part, so sine phi z cos omega t. So this will give me Vs by z, and by trigonometric formula, this is sine omega t minus phi z. So the same as with as I found in the time domain, okay, the steady state response. So this is the steady state response from the frequency domain derived. This is the steady state response of the series RLC circuit derived directly from the frequency domain analysis. And now I am going to show you the frequent and the circuit response of the parallel RLC circuit in frequency domain. And in the frequency domain, so by KCL, if I take the node voltage equation in the frequency domain, I will find IR plus IL plus IC equals IS. So this is in the frequency domain, so it will be, sorry, omega by s square plus omega square for the sine excitation, and I'm just writing it directly. So the equation, second order equation, the second order algebraic equation is, when rearranged, plus 1 by LC IS, sorry, Vs, which is equals Is omega by C S by S square plus omega square. So what I have to do is I have to find Is omega by C S by S square plus 1 by RC S plus 1 by LC S square plus omega square. And same way I'm gonna decompose this into partial fraction, s minus lambda 1 plus b, s minus lambda 2 plus cs plus d, s square plus lambda sigma s square plus omega square. So the a, b, c and d are basically the same. They're the same, exactly the same. I'm just gonna focus on this term, and these two terms are the transients introduced by the input in the parallel RLC circuit. So I'm not gonna I'm not gonna waste my time on this, because this is not that important. This third term is most important, the uh, transient part, sorry, the steady state part, and I'm gonna focus on that only. So before going to the steady state response of the parallel RLC circuit in frequency domain, let me first rearrange the characteristic equation. So s square plus 1 by RCS plus 1 by LC. So I'm gonna rearrange this plus 2, uh, 1 by 2 r root over L by C, 1 by root LC plus 1 by LC. So this is basically s square plus 2 psi p omega n s plus omega n squared. Now here if I'm gonna write this in factors, I have to find the roots, and similarly from the characteristic equation root, the eigenvalues in I found in the series RLC circuit equation. This will also be the similar case. So here s minus lambda 1, s minus lambda 2. Yes, so here lambda 1 equals to minus sigma p plus j omega d, and lambda 2 is minus sigma p minus j omega d, where sigma p is the damping coefficient for the parallel RLC circuit, which is 1 by 2 RC, and omega d for this is omega n 1 minus omega psi p square, psi p squared. So I'm just gonna occupy myself with only cs plus d by s square plus omega square is omega by c. So the expression for c and d are the same here also. So let me write it. So is omega c and 1 by omega square lambda 1 squared omega square plus lambda 2 squared omega square minus lambda 1 lambda 2 s by s square plus omega square plus omega lambda 1 plus lambda 2 omega by s square plus omega squared. So this is the steady state part for the parallel RLC circuit. I'm not focusing on the transient part. I'm only focusing on the steady state part because this is of most importance. So let's find what's the value of omega square lambda 1 square omega square plus lambda 2 square for the parallel RLC circuit. So if I carefully take this, this will give me 2 square minus 2 omega squared plus omega n 4. So this gives me this, and 4 sigma p squared omega square plus omega minus omega n square square square. So this will give me, so if I substitute for the value of the damping coefficient, it will give me omega squared by c squared by r squared, and if I take omega square of c square common, it will give me omega c minus 1 by omega l square. So which is basically omega square c square commoned out, and 1 by r square plus omega c minus 1 by omega l squared. So this is omega squared by c squared magnitude of admittance squared. So this will give me is omega by c and 1 by omega squared by c squared admittance squared, and this omega squared minus omega n squared, and if I take inverse Laplace I2s here also, it will give me it in time domain. So this will become cos omega t plus, so this will become minus omega 2 sigma p, the damping coefficient, sine omega t. So take this and is, and this will become c by omega y squared. And now if I take omega by c common from this, omega c minus 1 by omega l cos omega t minus sine, so minus this will give me omega by c r, sorry, omega by c r in the denominator, so 1 by omega t is is by omega c magnitude of admittance squared, and if I take the minus omega by c out, and I think there is also extra minus, there will also be extra minus, so I have forgot, so that I have forgotten it. So if you can check, there will be minus from the expression in the we found in the partial fraction of the equation. So this is obviously susceptance, sorry, so this is sine omega t by r minus omega c minus 1 by omega l cos omega t. Now what will happen is it equals, so this cuts out, so only leaving behind is by admittance squared, conductance sine omega t minus susceptance cos omega t. Then if I take the common out, it will leave me with, let us first write this, so g is y cos phi y sine omega t minus magnitude sine phi y cos omega t. So this will obviously give me is by, this is the magnitude, current magnitude of the current, and y, the square will be cut out, leaving y in the denominator, and by trigonometric identity formula I will get sine omega t minus phi y. So this is the same as the circuit response of the parallel RLC circuit we found, at least I found, in time domain. So there is also the transient part introduced by the input, and but I didn't derive that. It would have been uh, time consuming and it's kind of hassle, so I'm not dealing with that, because the steady state response is of more importance than that. So this is basically the expression for the parallel RLC circuit when the excitation is the sinusoidal input, and the excitation is the sinusoidal. So I hope you understood my explanation. So in frequency domain, the complex S domain, the circuit response for the parallel RLC circuit is the circuit response for the series RLC circuit for the voltage, sinusoidal voltage is current, which is in time domain we have found it equals the magnitude, sorry, the magnitude by, so this is the steady state response. Okay, I am not concerned with the uh, transient introduced by the input and transient for the initial stored voltage and current. So this is only the steady state part, and in time domain it will be Vs by Z minus by Z. This is in phasor form, and Z is R plus J omega L minus 1 by omega C, sorry, the magnitude, and which is magnitude and phi Z R square plus X square tan inverse X by R. And for the parallel RLC circuit, the uh, um, in frequency domain, for current, sinusoidal current input or the sinusoidal current excitation, the response of the parallel RLC circuit is voltage. I am concerned with the steady state response of the voltage. After analysis in frequency domain, the time domain expression becomes, after doing the inverse Laplace transform, it becomes the magnitude of the current, admittance, sine omega t minus phi y. So in the frequency domain it should be magnitude by y minus phi y. So this is approximately the phasor form in frequency domain, and y is g plus jb omega c omega l, which can be written also by this iy, which is g squared plus b squared tan inverse b by g. So this is the full expression for the series and parallel RLC circuit in frequency domain. I hope you understood. This is the steady state response. Okay, so I hope you understood my derivation and explaining, and I hope you like this video. So if you have liked this video, please join, subscribe my channel, and give a thumbs up. So thank you for watching.